So today let's start with the first section of properties of matter, and second half of the class we can keep some time for any doubts or questions pending in fluid mechanics. So if you have any questions from HC Verma or from the module that are pending, then you can keep them ready. We'll keep some time aside towards the second half of the lecture for discussion of questions. So the first topic within properties of matter we'll see is elasticity. So elasticity is a property for all materials or all matter such that when we tend to deform a body, okay, or take it out of shape by the application of some kind of external force, then on its own, the material or the body has a tendency to come back to its original shape when we withdraw the external force. And that tendency to retain its original shape and form is what we call the elasticity of the material. The most natural example is the action of a spring. Now, when we apply force longitudinally along the length of the spring to either extend it or compress it, it's in what we call a deformed state. But the moment we withdraw the external force, it has a tendency to go back to its natural length or its original state. So that property is because of what is called the elasticity of the metal with which the spring is made, or even the action of a rubber band for that matter. Okay. So in practical sense, all materials behave like that. Some materials are more elastic, some materials are less elastic. Okay, and some materials can also have a tendency to get very easily permanently deformed. That means they hardly show any elasticity. So like soft plastic or gum is an example of that. The moment we apply some external force to try and deform it, it has a tendency to remain in the deformed state. It hardly has a tendency to retain its original shape. But nonetheless, all materials have some amount of elasticity, whether that is in a large degree or in a small degree. All matter exists in such a way that there is this property whereby it tends to retain its natural shape, and that property is called the elasticity. So let us start with the definition. Okay, so elasticity of a material is the property due to which a body made of that material has a tendency to retain its original shape when it experiences a deformity due to external forces. So example, the elasticity exhibited by a spring on being deformed, that is either elongated or compressed from its natural shape, so in this case the natural shape is the natural length. A spring develops an internal conservative force, which is restorative in nature. And thus has a tendency to retain.
So F is equal to minus kx.
Yes. So that restorative force of the spring, or the tension that it develops, which is directly proportional to the deformity's extent, but opposite in direction. Okay. So hence the minus sign. So
Hooke's law.
yes, okay, that's Hooke's law applied to a spring. So that tendency is what we mean by the elasticity of the spring. Just make a note of this definition. So this is the natural length. Then we can, as you can see, we can elongate the spring, or we can compress it, as be the case, by the action of external force, which is like this. But on application of this external force, which will tend to elongate it, the spring develops its own internal conservative force. So this one is the restorative force. So this shows the property of elasticity. If the spring was made of something which did not have elasticity, so instead of a metal, if it was made of, let's say, soft plastic or something like that, then it would just remain continuously extended. It would not have a tendency to come back. It would not have a tendency of applying a restorative force to come back to its natural length. So this property of elasticity is it's extremely visible in the case of the spring. It's extremely pronounced, you can say. But even in other types of shapes and other types of materials, it is there to a certain extent. So for example, if you replace the spring with a metallic rod, on trying to apply external force on either side of the metallic rod, even the metallic rod will have a tendency to elongate. And as it elongates, it will have a tendency to apply a restorative force. Though it may not be so apparent to the, it may not be so apparent at a macroscopic level. Whereas again, in the case of a rubber band, or let's say a thin rod made of rubber, it might be much more evident to the naked eye that you apply some force and it immediately elongates, and there's a tendency to apply a restorative force. So we say that it's showing a larger extent of elasticity. But whether the extent is larger or lesser, all materials have a certain amount of elasticity.
Sir, what is X here?
X is the elongation of the spring. Its length has increased from L to L plus X, right? Okay, now another example of elasticity, for example, okay, is something like this. Suppose you have a solid block of rubber, which is kind of bolted to the ground. So it's fastened securely. So you have sort of, bolted it to the ground or attached it securely to the ground. And you try an experiment like this, that next what you do is on that rubber block, at this surface, you are applying some external force like this, tangentially at the surface. At the top surface, if you apply some external force like this, then you will see that it has a tendency to get bent like this. It has a tendency to bend like this. So we will see later in today's chapter that this is another type of deformity which is called shearing. The term shear, S-H-E-A-R. The term shearing stands for this kind of deformity where an object tends to bend. And it will develop an internal force, which again
Sir,
tries to
shear and strain.
yeah, shearing stress and shearing strain.
Yeah.
It will develop an internal force which is like this, which is trying to, it's restorative in nature. So this is another example of a deformity.
Tangential force upon area.
Yeah, that is the shearing stress, okay, particularly
Yes.
speaking. And the shearing strain is basically the angle by which it bends.
Yes, sir.
So we will come to these exact definitions and things, but no, so this is another situation in which what we observe is that there is elasticity of the material. It has a tendency to retain its original shape on being bent. So when we say, deformity, we don't mean only extension and compression. This is an example of shearing as a deformity, as a deformation. Whereas the above example of the spring, that was an example of elongation as a form of deformation. How we have deformed it from its original shape by elongating its length. Here, how we have deformed it by shearing it. So shearing it means we bent it at an angle with respect to the original shape. So if you take a plank of wood and you try to bend it like this, so as it bends like this, you can see physically, you can see it that it's undergone an angular kind of shape change, and that is again shearing. Of course, you know that if you put it under too much of stress and it exceeds something called the breaking stress, then it will simply break. It will fracture at a point. So I'm sure you've done all this as kids, taken a pencil and you kept applying force on it for whatever reason.
Yeah.
Whether it was you were trying to just release your physical energy on it, or you were just trying to experiment scientifically on it to see how far you can go before it will break or whatever. But you have experienced this, that the moment the stress, and I have not defined stress yet, but as you can understand, stress has something to do with the amount of force we are applying. So the moment the effect of the force externally applied on it exceeds a certain limiting value, the material just fractures or breaks. Just like as you're stretching a rubber band also, the moment you stretch it beyond the point, it will tend to fracture or it will tend to break from the weakest point of the rubber band. So excessive amount of external force can result in permanent deformation, can even result in breakage. But up to a certain limit, what happens is that the material retains its property of what we call elasticity. And that is that tendency for it to come back to its natural shape. And that property is what we call elasticity. Now let us understand where elasticity actually comes from. Why all materials I'm saying are elastic in nature, whether the extent of elasticity is very pronounced, like the case of a rubber band or a spring, or it's very less in comparison, that the elasticity is hardly visible, like a wooden rod. When you try to stretch it, you can hardly see it stretching. It will either break or it will be able to withstand the external force. But nonetheless, if you actually make proper measurements on it, you will see that there is elasticity. In fact, there is a very interesting experiment you can do to as an exhibition of elasticity. Try to measure your own height once while you are standing and once while you are lying on a flat surface, like lying on the floor or lying on your bed. Get somebody to measure your exact height to, let's say, millimeters or at least centimeters, and you will see that there's a significant difference. Can you guess when your height is more and when your height is less? Will it be less in standing position or less in lying position?
Stand.
Okay. Can you guess by how much your height is less? Have you ever done this?
No, sir.
No.
Okay, try it and see. You will see that it is less by at least a centimeter, and that is the effect of gravity. The effect of gravity on our body. Okay, our body is made of biological tissue and bones and all that, but they are all materials which have elasticity. So there's a tendency to get slightly compressed because of the effect of gravity. Whereas when you are lying on a flat surface, gravity is balanced by the normal contact force. So there is no tendency for any compression. So there is a significant difference which is quite measurable. You don't need any specialized equipment like vernier caliper or screw gauge or something like that to measure the exact change. There's a significant change in height. So if you want to ever entertain yourself that your height is the best possible measurement you can do, then please measure your height while you're lying down on a flat surface and not while you're standing. You can at least gain a centimeter or two from that. Okay. Anyhow, so next let's understand the origin of elasticity, which lies in the nature of matter in terms of matter at the molecular level. Okay, so origin of elasticity. Or intermolecular attraction force. So if you look at the interaction between molecules by looking at a potential energy diagram, where you're looking at the potential energy of a pair of molecules on the basis of their interactive force as a function of the distance between two molecules. So if you look at the graph of U versus R, where U is the potential energy associated with the intermolecular attraction, or you can just say the intermolecular interaction between two molecules. At a distance R. Okay, then it's a well documented fact that the potential energy diagram, something like this. So of course, negative potential energy shows stability. Positive potential energy shows instability. But there is also a clearly defined distance, let's say R0, at which the potential energy is minimum. And a local minima for the potential energy means that there is a stable equilibrium at that point. So that means two molecules undisturbed by external forces or external effects will tend to be in stable equilibrium at a certain amount of defined distance R0, which is what we call the natural bond length between two molecules. But because of any external cause, if we tend to bring the molecules closer than this natural bond length, then you can see we are increasing the potential energy of the system. So the direction of the internal conservative force, remember internal conservative force is minus du by dr. So you can see at R less than R0, the slope of this graph is negative. That means the direction of the force is positive. So it tends to repel. The two molecules will tend to repel each other if we try to bring them closer than that optimal distance of R0 or the bond length. Whereas on the other hand, if we try to pull them apart by bringing the distance larger than R0, then what tends to happen is that the force is now attractive. Now, it will be in the direction pointing in the negative direction, because the slope of this graph du by dr is positive at such a point. So the force which is minus du by dr will become negative. So you can see that at r equal to r naught, which is what we call the bond length, the system, by system we mean over here two molecules at a distance r, is in stable equilibrium. Therefore, any tendency of deformation by
Sir, can you explain the graph again, please?
by bringing the molecules to r less than r naught or r greater than r naught, okay, it results in restorative intermolecular force. Okay. So what the graph shows us that so if we look at potential energy versus distance graph, what it shows us is that r equal to r naught पे there is a certain minimum value of potential energy. So minimum of potential energy means there is maximum stability. Okay, remember one thing, that the lower the value of any potential energy u, the more the stability. Okay. Therefore, equilibrium is a stable equilibrium at potential energy's local minima. You remember this concept from work energy?
Yes, sir.
So what is the
Yes, sir.
relationship between internal conservative force and potential energy in a one-dimensional situation like this? It is minus du by dr.
Minus.
So wherever we are at the local minima, you can see slope is 0. So at this point, the slope of this graph is 0. That means the force is 0, the internal conservative force. But at a point like this, you can see when I brought it to r plus r naught plus r, let's say, or r naught plus delta r, let's say. So that means I brought the two molecules further apart from their stable equilibrium position. The slope is positive.
U is increasing.
No, and you can see slope is positive. So force is what type? It is negative. So instead of 0 force at this point, it will experience a force in this direction, which is, you can see, restorative in direction. Similarly, if I go to a point where I'm bringing the two molecules closer than r naught, so it's at r naught minus delta r. Now you can see at such a point, the slope of this graph is negative. So what about the direction of the force?
Decreasing.
Okay,
U
so
is
the
decreasing.
yes, u is decreasing. So that means the slope is negative. That means the force is which type? It is positive, because force is negative of slope. So now you can see now why the force is restorative in nature from
Yes, sir.
the shape of the potential energy graph. Because we have a stable equilibrium for this pair of molecules at the bond length. Okay, that means that if we try to bring the molecules, if we try to compress the molecules closer than the natural bond length, they will naturally have a tendency to come back to that r naught by restorative force. Or if we try to extend the system by bringing the molecules further apart from the natural bond length, again the internal forces of the system, that is the intermolecular interaction forces, which are basically as a result of what? Which are basically as a result of electromagnetism, because molecular interaction happens because of the interaction between
Strong
charged
nuclear
particles.
force.
Yes.
Strong nuclear.
No. Nuclear forces नहीं होते बेटा. Intermolecular force में क्या होते हैं? Electrostatic forces होते हैं.
हाँ,
No, it's to do with the chemistry of the atom. No? So it is all about the interaction between protons and electrons,
yeah.
right?
Yeah.
The nuclei and electrons. Nuclear forces kahan pe hote hain? When you go down to the nuclear level. Like
The
what
quark
keeps the
level.
nucleus intact, right? Even though there is tremendous electrostatic repulsion between
Yes.
protons. Okay, it is the nuclear forces that keeps the nucleus glued together. Okay.
Sir,
Yes.
so after R0, when you start taking after you start stretching the molecules apart from their position R0,
Yes.
so U
Yes.
tends to 0 but doesn't approaches, right?
Yeah.
Okay.
I mean, that is the general nature of the graph.
Yeah, so
In maths,
basically
it's called an
the limit concept comes here.
correct. You might have heard the term asymptote, no?
Asymptote, yes.
Yes,
हाँ,
sir.
Yes, sir.
हाइपरबोलिक ग्राफ में एसिम्पटोट होता है, काफी
Yeah.
सारे ट्रिग्नोमेट्रिक ग्राफ्स में एसिम्पटोट्स होते हैं. No?
Yes, sir.
So that's the thing, that as r tends to infinity, u will tend to 0. And on the other side, you can see there's a vertical asymptote. As r tends to 0, u tends to infinity.
Yes, sir.
So what that actually shows is that we can never actually bring the two molecules to 0 distance, because for that we need infinite energy.
Yes, sir.
Okay. So now we will learn about the different types of deformities.
Sir, please show that for a minute.
Okay. So, this is just to explain that in any system, when we are experiencing elasticity at the macroscopic level, macroscopic means when we are seeing it from a non-microscopic perspective. So when we are seeing it at the macroscopic level, whenever we try to deform a body, whatever the type of deformity, whether it is shearing or it is longitudinal, why the body tends to resist that deformity? Because if you look down, if you magnify, or if you look at it at the through a microscope at the molecular level, what is happening? This is how the molecules behave. If because of some external forces you're trying to bring the molecules, you're trying to extend the material or increase its dimension, its geometric dimension, that means you're trying to pull the molecules apart from the normal or the natural bond length. So immediately the intermolecular interaction is such that at the intermolecular level itself, there is some kind of internal force which tries to restore the molecules back to the natural bond length. Similarly, if externally we are trying to compress the shape of the material, then again at the molecular level, what's happening? We are trying to force the molecules to come closer than their natural bond length. So automatically the electrostatic interaction that is there between the molecules, because after all, molecules are made of atoms and atoms are made of charged particles. So there's some kind of balance between the electrostatic forces between the various charged particles. So that balance gets disturbed. So the balance always gets disturbed with the tendency to restore back to the balance. So when we try to bring the molecules, force the molecules closer than their natural bond length, the intermolecular forces will act in such a way they try to restore back the balance. to the stable equilibrium position of bond length. So it is this nature of matter at the very molecular level, at the most fundamental level, that shows up at the macroscopic level as the property of elasticity. And that is why, as I told you, all matter ultimately has elasticity. I mean, believe it or not, but if you take something like very weak material, like a thin piece of paper, and if you were to do measurements at a very intricate level, measurements at a very sensitive level for any dimension of the piece of paper, like the surface area or the length of the piece of paper or something, and you put it under very less amount of stress, not enough to tear the paper or anything like that, you will see that it will get stretched. And the moment you release that external force, it has a tendency to come back. Or for example, if you see a piece of paper flying in the wind, continuously you're seeing the shape of the surface contorting with the wind. But as the shape of the surface contorts, if you were to actually measure the surface area instant to instant, you'll see there are minor changes in the actual surface area, because it is actually acting like a rubber membrane would act when it is under push and pull. It will have a tendency to alternately stretch and compress, stretch and compress. So even something that one doesn't think intuitively that paper is a material that can show elasticity, but if you look at it at a very microscopic level, it will show elasticity, because ultimately it is made of molecules, and all molecules behave in this way. Okay. So it is just that the elasticity is very pronounced and very visible in certain materials, and that is where the properties of material comes in. That's where our description of properties of materials to various types of physical quantities, like you would have heard of modulus of elasticity. So modulus of elasticity is going to be a physical property that we'll define, which helps us understand, which helps us classify materials, that which ones are more elastic, which ones are less elastic. Okay. Then there is elastic strength. Okay, another measure of the property of elasticity. There is breaking stress, which is a measure of the amount of stress a material can withstand before it gets destroyed from its property of elasticity, and rather it fractures or breaks. So that is the ultimate in permanent deformation. If we actually cause a physical object to fracture or break, then it's showing the complete opposite nature of elasticity. It's permanently deformed in the form of fracture, right? So all this starts at the molecular level because of the nature of intermolecular bonds. And if you ask, okay, why is the nature of intermolecular bonds like this? The answer to that is it's the very nature of fundamental particles of physics, like electrons, protons, and how they behave with respect to each other because of their fundamental property of charge. So it all comes down to the relationship of the four fundamental forces known in physics. That is gravitational force, electromagnetic forces, nuclear forces, and weak forces. Everything that we know of the physical universe around us is a result of some kind of interaction which has to do with combinations of these four fundamental types of interaction. So when we talk about intermolecular interaction, obviously we're talking about electromagnetic interactions, that is interactions between the charged particles, because molecules consist of fundamental particles of physics which are charged in nature. All right, now we will look at some different types of deformations, and then we'll come to stress and strain. So when a material undergoes a deformation whereby its length is altered with respect to its natural length by either compressing or extending it, then it is called longitudinal deformation. So longitudinal deformation is of two types: compression and extension. So if we apply external force in this way, such that it is now experiencing an elongated state, or that is a type of longitudinal deformity. Or by applying external force like this, we are making the body or making a certain material experience a compression. So compression is also a type of longitudinal deformity. Whereas here, this is in its natural shape. because L is what we call the natural length when it is not under the action of any external force. So that's also a form of longitudinal deformity. So any change in a length parameter is a longitudinal deformity, and longitudinal deformity is measured by something called longitudinal stress. Sorry, longitudinal strain, not stress.
So what's
So
the main
strain is a
difference between
term.
stress and strain? I'm thoda confused.
I'll explain it. Okay. So when we are talking about deformity, any deformity is measured by a parameter called strain. A strain is a parameter that defines or that measures the amount of deformation. So longitudinal strain is just defined as the fractional change in length with respect to the original length. So in general, the term strain is used to measure the amount of deformity. Okay. And then depending on the different types of deformations, we have different definitions for the according amount of strain. So when we are talking about the first type of deformity, which is longitudinal deformity, then accordingly, to measure this type of deformity, we have a term called longitudinal strain. And how we define the longitudinal strain, it is the fractional change in length. In words, we will say it is the fractional change in a length. Okay, is called the amount of longitudinal strain. Okay, is it clear what strain means in general? Okay. Now, additionally, you can see that strain is a dimensionless quantity or a unitless quantity, because it's always a fractional change. Whereas stress is something else. Stress is, we'll see, it always has the dimension of force per unit area. So when we say how much is the strain the body is undergoing, so basically we are trying to measure how much it has got deformed and how we measure it mathematically. So in case of longitudinal strain, we measure it mathematically as the fractional change in length. So if a 5-meter rod has undergone a 1 centimeter extension, then we will say the strain is equal to 1 centimeters divided by 5 meters. So that's 1 by 500, or that is 0.2%. Okay, or 0.002. Okay, so let's write that down as a numerical example also. For example, if a rod of natural length equal to 5 meters is extended by delta L equal to 1 centimeter, then the longitudinal strain is under, that will be equal to 1 upon 500, because it is 1 into 10 raised power minus 2 divided by 5. So 1 by 500, or as I said, that is a 0.2%. So generally we don't express strain in percentage, we express it just as a fraction. So you can say it's a 0.2% change in length, but as far as the definition of longitudinal strain is concerned, we express it in fractional form, not in percentage form. So we will say it's undergone a longitudinal strain of 0.002.
Sir,
Yes.
Sir, can I just
was there
single
anything
from-
else written before this?
Sorry, come again, Beta.
Was there anything else written before this?
Is there anything
Else written before this?
before types of
T?
deformity?
Yes.
No, we were just talking about the intermolecular this thing, no? The nature of intermolecular bonds, okay, and the origin of elasticity. Right? Did you get this part?
No, I'll take it later.
Yeah. Actually, you got disconnected, is it?
No, I came late.
Oh, sorry. Yeah, I'll send you the notes. Okay. Don't worry. So this is the first type of deformity. Okay. It is called the longitudinal deformity. Okay, so this is clear, I hope. Okay. Now the second type of deformity, it is what we were discussing about earlier. It is called shearing. And it is measured by the term
Sir, can you
shearing.
scroll up for 1 second?
Yeah. The term shearing strain is a measure of the amount by which the body is under a shearing type of deformity. Okay, I'll just scroll back up to you.
Yes, sir, done.
Okay. So shearing is the term that we use when an object bends from its natural shape. So one example I had already shown you earlier, that you have, let's say, an object like this. And then you tend to subject it to some external force. So as a result of that, if you apply force in this way, the body will tend to change its shape like this. So it has got shear. Or if you have an example like this where so you have something like a rod which is fastened to a wall like this. This is the natural shape. And now what we do is we attach some weight to the end of the rod. So we'll see that in general, tend to be a little bit bent like this. Put some weight over here. So you can see that this is called the shearing strain. So shearing is defined as a bending from natural shape. So because this angle is small, we can also sort of measure it as like if this is X, okay, and this length is L, then it's approximately equal to X by L because it's a small angle. So we can approximate theta as tan theta. Okay. So similarly, in the case of the first diagram, if the natural shape of this block was like this, length was L, Now when we bent it out of shape, it's become like this. The angle by which we bent it, that becomes the shearing strain. And as you can see, it's a dimensionless quantity because it's an angle. So it's a unitless or a dimensionless quantity. So upon applying a force like this, it's bent through an angle theta like this. Okay. So again, if this distance here is x, okay, then typically the bending angle is very small. So we can approximate theta as x by L. So just make a note of this, people. So a type of deformity where the material, instead of compressing or extending from some natural length, it's undergoing a bending. It's bent out of shape. That is called shearing. And the extent of shearing, the amount of shearing or the amount of deformity is measured by the angle by which it is bent. Okay, so shearing is clear to all of you. Okay. Yeah, the original formula for strain, for shearing strain, is the angle of the bending, which is theta. But it can always be approximated as x by L because theta is a small angle. Okay, so tan theta will be approximately equal to theta, and tan theta in the diagram you can see is about x by L. or even when it's like a circular bend, like in the second diagram I've made, it's arc upon radius. So x is almost this arc length because theta is a small angle. So this approximation is done because theta is a small angle. So it's a small angle approximation. So small angle approximation is like this, that tan theta is approximately sine theta is approximately theta is arc upon radius. Okay, the third and final type of deformity is what we call a volume strain. Or voluminous deformation. So that is when there is a compression or extension or expansion in the volume of a body. Okay. So for example, let's say you have a rubber ball which has a natural volume V0. Next, what you're doing is you're taking this rubber object and placing it under water at a pretty large depth. So particularly if the rubber is reasonably soft, you will observe that there's quite a sizable change in its volume because of the extra pressure, which you know is called hydrostatic pressure. If I take this same rubber object and take it to a certain depth, so you'll see that due to the excess pressure, B would have become less than V0. It was compressed due to the hydrostatic pressure. So that's an example of an object undergoing a voluminous strain or a voluminous deformation. So like that, if we take it to a great height above the Earth's surface, where the pressure becomes considerably less than the standard atmospheric pressure at the surface of the Earth, then it might experience an expansion. Okay. So either case, we say it's undergoing a voluminous deformation or a volume deformity. Okay, and volume deformity is measured by something called volume strain. And the formula for volume strain, just like longitudinal strain, it is the fractional change in volume.
सर आप वो वाला जिसमें वॉल्यूम एक्सपांड हुआ बॉल का
Sorry?
यू सेड सर कि अपने अगर हम लोग उसको कोई तो एक्सट्रीमली दूर रखेंगे कोई जगह
हाँ, मतलब as you know ना, the atmospheric pressure decreases with height above the Earth's surface.
हाँ
Because basically atmospheric pressure कहाँ से आता है? It comes because of the fluid pressure of air ना. Gas is also fluid. So as you go above the Earth's surface, the height of the atmosphere above you becomes lesser, no? So atmospheric pressure decreases. So if you take a soft object like a soft rubber ball to a significant height above the Earth's surface, you will actually see it expanding because pressure has become less on it, no? Understood the point? No? Just like यहाँ वाले example में, how I have compressed the rubber ball by increasing the pressure on its surface, no? The pressure on the Earth's surface was atmospheric pressure. Now, at a depth of D below water, the pressure is increased by how much? Rho GH, where H is the depth of, so like that. So like that, instead of increasing the pressure and thereby compressing the volume, if I do something to decrease the pressure, or I might put it in a, in a pressure chamber and start pumping out air. So air pressure will decrease on it. So again, I will see the rubber ball expanding, or I might take it to a certain height above the surface. So atmospheric pressure has naturally decreased. So again, I will observe the opposite of this particular experiment, which I've shown in the diagram. I'll observe the opposite of this, that when I reduce the pressure on the rubber ball, the effect is that its volume expands. So now the thing is that whether the volume expands or it compresses, the extension of the strain, the amount of strain is equal to nothing but the fractional change in volume. That is called volume strain.
Okay.
So the extent of deformity it has undergone is measured as what we call volume strain. Just like for a longitudinal deformity, the extent of deformity is longitudinal strain. And for a shearing, it is a shearing strain. Okay. So all three are dimensionless quantities, but one is fractional change in length. The other is the angle by which the object is bent. And the third is the fractional change in volume. So each type of deformity has a related type of strain. And the strain is nothing but a measure of the amount of deformity as a physical quantity which is unitless. Okay, so the definition of strain in all three cases is clear, I hope. Okay. Now next we will talk about a physical parameter called stress.
Sir, 1 minute.
Okay.
Done, sir.
Okay. So strain, as you can see in all three cases, whatever the type of deformity, strain is something that we use to measure the extent of deformity. Like if we are comparing two bodies which have undergone the same type of deformity, how we'll know that which one is more deformed? The one which is having more deformation is the one which is having a larger value of strain. Okay, so as simple as that. But of course, we cannot compare one which has undergone shearing with respect to one which has undergone longitudinal strain, because they're two different type of strains. The direct comparison is only possible if we're talking about longitudinal strain of one object with respect to longitudinal strain of the other, or we're talking about shearings in one with respect to shearing in the other. But given that, how do we compare mathematically? We compare by measuring the amount of strain, which is nothing but a unitless quantity. Typically, it is a fractional change, but in the case of shearing, it is the angle by which it's bent. So even that angle can be expressed as a fractional quantity. As you can see, it's x by L. Okay. So anyhow, now next let's see what causes strain in the first place. What causes a body to get deformed? And that is nothing but stress. Okay, so how we define stress? You can think of stress as something that stress describes the effect of force on a material such that it creates deformation or strain. So whenever an external agent is applying some kind of action on a body in terms of an external force, we will be able to define some quantity on the basis of force which has the effect of the body getting deformed. So that quantity that we define in terms of whose basis is the force, and that is creating the deformation of the body, that is called stress. Okay. Stress has the dimension of force per unit area. As I told you, the basis of it is force, but it is not equal to force. It depends on the amount of force, okay, stress. So its dimension is force per unit area, or stress is expressed in newtons per meter square. Now, different types of stress create different type of strains. Okay. So to create a longitudinal strain, okay, or deformity, the type of stress in action is longitudinal stress. So you can say, for example, so now let's look at the different types of stress. So the first type of stress is longitudinal stress, also called tensile stress. Okay. So if you hear the term, tensile stress, you know it's the same thing as longitudinal stress. The term tensile is actually coming from tension. So longitudinal stress is defined as tension per unit area of cross section. The tension force in a longitudinal body. Okay. The typical example of this is, let's say, we have kept some kind of a rod under the action of some external force, like this. So as a result of that, the rod has got elongated. But as you also know, the rod develops an internal tension, which acts restorative in nature. So this is the tension, that is an internal force acting along the length, and A is this area of cross section. So if this rod has this area of cross section, so for example, if I have a rod of uniform cross sectional area, okay, and two equal but opposite forces are acting at either end of it, then we know that there's a uniform tension at every point, and the cross sectional area is also uniform. Then the longitudinal stress at every point inside the rod will be uniform, because it's the same amount of tension divided by the same amount of area of cross section. Yes, you have any doubt, Beta?
Sir, can you explain again?
Yeah, the definition of longitudinal stress, it is tension per unit area of cross section. Okay. So whenever a material is under some kind of longitudinal strain or longitudinal deformity, it is because some external forces are used either to extend it or to compress it. So that will create the internal force of tension which acts along the length of the rod. So that internal force of tension per unit cross-sectional area, that is what we define as longitudinal stress. Is it clear?
Okay.
Okay, make a note of this, please. So Sujal, to answer your question, in different types of deformity, we define different types of strain and accordingly different types of stress. So in case of longitudinal deformity, we define longitudinal stress and longitudinal strain. So longitudinal stress is defined as tension per unit area. Longitudinal strain is defined by fractional change in length. So like that for shearing, we will define shearing stress, and you've seen shearing strains deformity. Like that for volume deformity or voluminous deformity, you've seen we've already defined volume strain. We'll also define something called volume stress. No, Varun, to answer your question, T will not be equal to F external always. Okay, it is subject to certain conditions. Okay, so we'll come to that. Okay, in numerical problems. So let's look at a numerical example. So suppose we have something like this. We have used a very thin metallic wire, which is quite light, but we used it to suspend a heavy block. So this is so it has a cross section of, let us say, 5 millimeters square. So it's quite thin. Okay. And it's extremely light. So we can treat it like massless. And now we use that to suspend a heavy block. Say 50 kg block. So in this case, what will happen is that because the wire is massless, or we can treat it as massless, the tension is uniform. Okay. So that uniform tension will be equal to the weight of the block. So that will be 500 newtons. Okay, so therefore at any point in the wire, there will be a uniform stress, longitudinal stress. Therefore, the longitudinal stress is uniform, and it is equal to this value of tension divided by cross-sectional area. So it is 500 newtons divided by 5 millimeters square. So I can write it as 500 by 5 into 10 raised power minus 6 in Newton per meter square. So as you can see, it is 10 raised power 8 Newton per meter square. So there is a uniform longitudinal stress at all points, which is equal to this. But of course, that is happening because this is massless, because we can treat it like massless because it's extremely light and it has a uniform cross section. There's a uniform cross section like this. Okay, now we can always have a situation where the stress is not uniform. The most obvious example of that is if you have a heavy metallic rod like a pillar hanging under its own weight. So as you know from mechanics, there will be variable tension in it. Okay. Variable tension and therefore non-uniform stress. And by stress here, I mean longitudinal stress. So I'm taking this example of it. So let's say this is like a heavy metallic cylinder which is suspended from some ceiling. So its mass is m. The uniform cross section is A. Okay. Now the first thing we'll do is if we consider some point like this, which is at a distance x from the bottom of the cylinder or pillar, we want to find tension T at a general point P at distance x from the lower end. So basically this tension we'll be finding will be a function of x. Okay. And from that we can find the longitudinal stress at the point P, again as a function of x. So this could be a situation where we answer the question that we just discussed, that is it necessary that tension is uniform at all points? Definitely not. In fact, it's only in certain cases, certain special cases, that we can say that a material is under uniform tension while it is in a longitudinal deformity state. Just work this out, I'll join it. Yeah, so can you send me the answer of the first part? What is tension as a function of x? Remember how we had done this in mechanics earlier in Newton's laws of motion. What you do is you make a free body diagram of this section of the rod or pillar or whatever. You can sort of mentally break this into two parts. So if this is the section of length x, this is the section of length L minus x. So whatever tension is acting like this, equal and opposite tension is acting over here like this. And let's say the tension at the uppermost point is T0. Now, let's say this one has a weight of mxg. And this has a weight of, where this is mass per unit length into that distance. So the mass of the upper part is the same mass per unit length, but into x minus L. So you can see that from the first FBD, we can see that T naught will balance T plus, or from the second FBD, see T will balance with this. So this becomes your answer. Okay. Now also, if you make the full things FBD, then you can see that the tension at the topmost point T naught is actually balancing the full thing's weight. So from this you can show that T naught is equal to mg. So if you substitute that here, you will get this for T. There are two ways of justifying this equation. So there's nothing extraordinary here. It's just basic mechanics that we're talking about. Okay. So now from this we can see that the tension as a function of x is becoming mg by L into x. And so it's a linear function of x. So now accordingly, the stress, the longitudinal stress at any point will become tension divided by area. Now area of cross section is uniform. So that will, the longitudinal stress will also be a linear function of x. Okay, so like this, there are many different types of examples. Okay, like we could have a situation like this where, for example, we have an odd shaped kind of metallic rod, which is kind of tapering in shape, let's say. Okay, so maybe this end is like this only, but this end kind of tapering in shape. So this is a metallic object which we have kept fixed to a wall. Now what we are doing is we are pulling it with some force like this. Okay. So if the area over here is A1 and the area over here is A2, you can see that the stress at the 2 points will be different because the area of cross section is different. Okay. This is supported by some horizontal surface, so the weight is not a problem. The weight is balanced by normal reaction. So it's like a bullet shaped kind of thing, you know. So it's attached to a wall over here. So let's say we are applying a force of 50 newtons. A1 is, let's say, 10 millimeters square, and A2 is, let's say, 5 millimeters square. So if this point is P1 over here, and this point is P2, so find the longitudinal stress at P1 and at P2. So you'll see that it is different. So even though the tension is uniform, okay, so the metallic object is experiencing a uniform tension. Okay. But stress at point 1 you can see that okay, this is double of this. Stress at point 2 is 2 times because the area is half.
Sir, could you please go to the previous question for a second?
No, Shikhar, it doesn't matter whether it's massless or not. Na? Dekho, kya hota hai na? When we keep an object like this, whether its area is uniform or not, the weight is balanced by normal reaction. Okay. So for example, if the force is F over here and the tension at this end is T1, so you can see that because the acceleration of the object is 0, so T1 is equal to F. Okay. Now imagine you've broken this rod into some bit like this. Now you make the FBD of this section. So at this end, the tension is T1. At this end, suppose the tension is T2, or the other part of the rod, T2 and F. Okay. So this is of length X, this is of length L minus X. But again, the horizontal forces have to balance now. You understood now? So in this horizontal case, it doesn't matter whether the rod is heavy or light. Okay. T1 is equal to T2 is equal to F. So therefore, it has a uniform tension. Everyone. Is this clear, Shikhar?
Yes, sir.
Yeah, okay. Yeah, Jagannath, I'll go up. Previous part.
Done, sir. Thank you.
Okay. Now we come to the second form of Hooke's law. Hooke's law that we had seen earlier was defined for it was defined for a spring. Okay, but the general equation of Hooke's law in elasticity of all materials. So Hooke's law is an experimental law based on the study of elasticity of different materials. So it's an experimentally derived principle related to elasticity and defines a relationship between stress and strain. So in general, that relationship is that stress is directly proportional to strain up to a certain limit of stress, okay, called the elastic limit. Now, beyond that, what happens, we'll discuss later. Okay, but as long as the stress is up to a certain limit, called the elastic limit, stress and strain are proportional. So now, specifically speaking, Hooke's law for longitudinal deformation is that stress and strain are proportional to each other, but which stress and which strain? Longitudinal stress. The longitudinal stress, its ratio with respect to longitudinal strain is a constant called the Young's modulus of elasticity. Just a moment, guys. Yeah, sorry about the interruption, people. So continuing here, so the ratio of longitudinal stress and strain is a constant. Okay, and that constant is called Young's modulus of elasticity. So this is a constant, which is a material property of the material with which the body is made. Okay. So irrespective of the shape and size of the object, like the metallic pillar we were talking about earlier, irrespective of the area of cross section and the length, or the steel string that we are talking about, okay, or the thin wire we are talking about, irrespective of its natural length and irrespective of its area of cross section, the modulus of elasticity just depends on what it is made of. So steel has a fixed value of Young's modulus of elasticity. Copper has a fixed value of Young's modulus of elasticity. Like that, all other materials have a fixed value of this particular elastic property, which is called the Young's modulus. So Young's modulus is nothing but the ratio of stress and strain. Okay, provided, of course, so this condition, that this equation that we are writing, so we can write it like this, that stress upon strain, that's how it's written, that's equal to Young's modulus. Longitudinal stress is defined as tension per unit area. So this is how we express it in terms of an equation. So where A is cross-sectional area, T is tension. So T by A is nothing but longitudinal stress. And delta L by L is nothing but longitudinal strain, which is the fractional change in length. So another way to express it is that stress is directly proportional to strain. The statement of Hooke's law. And the constant of proportionality here is the material property which we call Young's modulus. But this is for stress less than a maximum limiting value called elastic limit. So we'll discuss more about elastic limit in future. Okay, first we will understand the application of Hooke's law. Now, one additional thing that you can observe from this equation of Hooke's law is that Young's modulus has the same dimension as stress, because strain is dimensionless, which is the dimension of force per unit area. Okay. So Young's modulus is expressed in newtons per meter square. And typically, metals have Young's modulus order of magnitude 10 raised power 11 Newton per meter square. So like all material properties, Young's modulus is something that we measure from experiment. Okay, empirically from experimental data, the values of Young's modulus for different materials is measured, and then it is, typically it is published in engineering manuals, because we need the value of Young's modulus in engineering design. Now, for example, if you are using steel cables in a suspended bridge design in civil engineering, then you need to be able to understand how much strain that steel cables will be under, for what kind of loading of traffic you are expecting. So to understand that strain versus loading of traffic, you need to understand the dimensions of the steel cable that you are using, as well as the property of steel, which is the elasticity. So that elasticity of steel will be measured like with serious statistical analysis done on a whole lot of data from whole lot of experiments done using steel and measuring its elasticity. So if you look at typical engineering manuals which deal with elasticity and material properties, you will see there's an entire list of standard type of materials, including metals and non-metals, for which the elasticity in terms of Young's modulus of elasticity is published. So, for example, if I'm not mistaken, copper has a Young's modulus of, I think it is, I'll just check and tell you, I think it is something in the region of about 2 Newton per meter square. Whereas if you look at something like steel or nickel coated steel, okay, or nickel based steel, it is a higher value of Young's modulus. It's in the region of 3.5 into 10 raised by 11 Newton per meter square. So you don't need to remember any values of Young's modulus. Just giving you an example here. So interestingly, of course, Young's modulus varies a little bit with temperature. Okay. Sorry, copper is about 1.2, not 2. It's approximately 1.2. For example, iron has a Young's modulus of about 2.1. Steel is more like 2.8. Whereas, for example, bone, Young's modulus of bone is about this much. So order of magnitude is 10 raised power 9. Anyhow, so let's conclude today's session with a typical example of the values of stress and strain involved in that type of situation we were talking about earlier, where you have a thin metallic wire used to suspend a heavy object. So it has typically something like a uniformish kind of tension. So therefore uniform stress. So let's take that example only, where we've taken the mass to be 50 kg. Now let's say this is a metallic wire. It has a uniform cross section of 5 millimeters square. Okay. And it has a natural length of, let's say, 2 meters. And the Young's modulus of the metal is, let us say, 3 into 10 raised power 11 Newton per meter square. So in this case, it will be an elongated kind of shape or elongated state. So we have to find the tension, the stress, and the strain. Not, in fact, not the ratio of stress and strain, but stress and strain separately. By that we mean longitudinal stress and strain. And from that we have to calculate the extension, how much it is. Okay. Take G as 10. So how much does this thin metallic wire get extended? Yeah, Newton per meter square. That's correct. The unit of Young's modulus will be Newton per meter square, because that is the unit of stress now. Force per unit area, na beta. Stress upon strain is equal to Young's modulus. So you can see dimension of Young's modulus will be dimension of force per unit area. Durgesh and Samar, the unit is clear, no? I think I've written unit correctly only, no? Newton per meter square. Yeah. Okay, so let's work this out quickly. So we can see that the tension is a uniform value of 500 newtons, taking G as 10. Okay, so the stress, the longitudinal stress is 10 raised power minus 8 Newton per meter square. So now
So
the
10 to the
strain,
power 8, huh?
So
so
plus
10
8.
to the power 8, yeah. So the power plus 8, yes. So the longitudinal strain, how we'll calculate that now? Delta L by L, we'll use Hooke's law. That longitudinal stress upon longitudinal strain is equal to Young's modulus. Okay. Or in formula, we can write that E by E divided by delta L by L is equal to Young's modulus. So you can see that the strain is actually the stress divided by the Young's modulus. So the stress is, we just saw, 10 raised power 8 newtons per meter square. And the Young's modulus is the property of the metal which is given to us. 3 into 10 raised power 11. So you can see 1 by 3 into 10 raised power minus 3, or we can write that as 3.33 into 10 raised power minus 4. So that is the strain. Okay. Now, once we got the strain, from this we can calculate the extension. Delta L by L is equal to 1 by 3 into 10 raised power minus 3, or 3.33 into 10 raised power minus 4. So what is the extension? Delta L is whatever the natural length was into the strain. Okay. So the natural length was 2 meters. So it's becoming 2/3 of a millimeter or 0.67 millimeters. So that 50 kg block will stretch this 2-meter long cable by less than a centimeter, by 2/3 of a millimeter. Sorry, less than a millimeter even, 2/3 of a millimeter. So this is, the actual kind of experimental value you can expect if you were doing this in the physics lab. There are some demo videos in YouTube also of, these kind of experiments done for stress versus strain. Okay. So maybe you can refer to some of them at a later stage, but the application is very simple. As you can see, it's quite a formula based chapter. So anyhow, we'll conclude today's session here, and next time we will conclude this part of elasticity by also understanding the application of Hooke's law in the other two cases, that is the shearing and the volume stress and strain. So we'll see the definition of shearing stress, we'll see the definition of volume stress, and then the application of Hooke's law, okay, in those two cases also. Oh, Samarth, you were asking about that. Yeah, Young's modulus actually reduces with increase in temperature. It's not a directly inverse proportionality, but the Young's modulus of materials tends to tend slightly, because materials tend to weaken. Okay. So that's why you will see in a standard engineering handbook, the Young's modulus of different metals are typically given at room temperature and then at some different temperatures also. So you know that if you're designing a structure at where the operating temperature is expected to be a certain value, then accordingly what is the Young's modulus in that situation. Anyhow, so yeah, Jagannath, I'll do that. Okay, so we'll conclude today's session here, people. Wish you all the best. Okay, thanks for attending.
Thank you, sir.
Thank you, sir. Bye, sir.
Okay,
Thank
bye.
you, sir. Bye, sir.
Bye.
Sir, could you please move down to the graph? Hello, sir.
Jagannath, you are there, yeah? Jagannath?
Yes, sir, I'm there, sir.
Okay, so I'll share it. Sorry, I was. So this part you wrote down, no?
I wrote the blue paragraph. Could you scroll down?
Yeah. Next thing after this, just a moment. Okay, so the second example of elasticity, and then we saw some types of elasticity.
So here,
Yeah.
the elasticity tends to zero, right? Tends to zero when it's increasing, when the R is increasing.
No, elasticity doesn't tend to zero, beta. At R equal to R naught, now what
Sorry,
is happening?
it tends to zero.
Is tending to zero as R tends to zero. U is the potential energy.
So then maximum is infinity, right?
Yes. Okay, Jagannath, done?
Sir, I'll just take a picture then.
Okay. I will send you the this thing also. The notes also. After this, you had attended, no?
Yes, sir, I had attended after
From
this,
types of.
from types of deformations.
Okay. Okay.
Thank you, sir.
Okay, then. Okay.
Bye, sir.
Bye.